So this is a table comparing solids, liquids, and gases, and we've talked about these things before. So here we're looking at the three states of water. So we have gas, we call it steam, liquid water, and solid ice. Here's illustrations of what this would look like. So here we have the water molecules, but they're very separated from each other. And here in the liquid, they are touchingly close, but they can swim around, they can mingle around and move. When it's frozen, those molecules are also touchingly close, but now they cannot move relative to each other, and that's why the solid keeps its shape. Okay, so here the molecules are very far apart, and so the density is very low because there's a lot of empty space. The liquid and the solid have densities that are very similar to each other because there's not very much empty space. The big difference between solids and liquids is how those particles can move relative to each other. And I've mentioned the solid, liquid, and gas state of students, right? We're in lecture right now, everybody's sitting nicely in their stools at the benches, you're in the solid state. Everybody's moving a little bit, breathing at least, but you're not moving around the classroom. But during lab, we're going to be in this same space, but now we're going to move around, and that's what a liquid does. The particles are still close. You can reach out and touch someone, right? But you can also move around. So we see that in a solid, solids and liquids are both going to have high densities because the particles are close together. A solid will have definite shape. So if you think about an ice cube and you pop it out of the ice cube tray onto the counter, does its shape change? No, it keeps its shape, right? Solids keep their shape. So that's a definite shape. What about liquid? Liquid water. If you take liquid water that was, in a cup, or maybe that same ice cube tray, but you left it out and it melted, and you dump it on the counter, is it going to still be shaped like the ice cube tray? No, it's going to spread out, right? Liquids have indefinite shapes. Gases also have indefinite shapes. They take on the shape of their containers. And then volume. So a solid is going to keep its same volume no matter what kind of a container you put it into. A liquid will also keep the same volume. If you pour that liquid into a larger container, it doesn't get bigger, right? But gases have indefinite volume. If you take a gas sample and you put it into a bigger container, it spreads out until it fills up the whole container. And that's a very weird thing the gases do. And these properties here all come from these intermolecular forces. So at any given temperature, a gas would have weaker intermolecular forces holding those particles together. It's not being really successful. And the liquid would have moderate strength, and the solid is going to have strong. So this is kind of what I already said. Liquids will take on the shape of their containers. Gases are compressible. They're also expandable. So if we have a piston here and it has a liquid in it, we can push down on that piston, but we can't compress the liquid anymore, right? Whereas if we have a gas and we push down on that, we can squeeze those molecules closer together because there is empty space in between. When we talk about solids, we can talk about different categories. There are crystalline solids and amorphous solids. So in a crystalline solid like this one, there's a regular and ordered structure for how the particles are next to each other. So this is like, students sitting in rows of desks, right? They're all in nice rows and everything. This is called amorphous, meaning literally without shape. So this is all jumbled together. So this is like in the kindergarten class, and the teacher says, okay, kids, come up here and sit on the floor. I'm going to read you a story, right? Do they sit in straight rows? No, of course they don't. They're just jumbled all over the place, right? So that's amorphous. So this is a question you should be able to answer on an exam. Which state of matter is compressible? A gas. Changes between states. Okay, we're familiar with the changes in the states of water. We've got ice that melts into liquid water. Liquid water can evaporate or be boiled into steam. These changes in state happen due to temperature. So what happens here is, as we increase the temperature of that substance, the thermal energy is growing where the intermolecular forces are not changing. And so now as it heats up, now that thermal energy is able to partially overcome the forces that are holding the particles together, and so it melts and becomes a liquid. If we continue to heat it, adding more energy, now those particles have enough energy that they can completely break loose from their neighbors and just float around independently. You can also transform a liquid into a gas by reducing the pressure. And then, of course, the opposite is true. If you take a gas and you cool it down, or you compress it far enough, it will condense into a liquid. If you cool a liquid, it will become a solid. This is an illustration of a propane tank. So LP gas is mostly liquefied propane. LP stands for liquefied petroleum gas, not propane, but it's mostly propane. So here are little propane molecules. And this is under a great deal of pressure. That's why they don't want you to take those into the store, because if it's going to explode, they'd rather it do that outside. So you compress that gas until it becomes a liquid, and you've got a valve up here. Now, there's always going to be some space above the liquid. It's not going to be absolutely full. And so what's going to happen here is you're going to have some of this in the gas state. When you open the valve, that's going to allow some of these gas particles to escape, and those will be replaced by liquid molecules escaping into the gas phase. So it's just evaporating. The reason we use liquefied petroleum gas is because it takes up so much less space than if we were just going to cart around a gas. So here we have a diagram showing liquid water. And this is asking us, which of these pictures best illustrates what you would get from a pot of boiling water? So when we boil water, is that a chemical reaction? A chemical change? No, it's a physical change, right? It's water going from a liquid to a gas. Does that change the particles? No, the molecules are the same. So when this becomes a gas, we should still have these little Mickey Mouse water molecules, right? So which one is that? That'd be A. The molecules are the same. What's different is that they're further apart from each other and they're no longer interacting with each other.